Okay, so now we're into energy, right? This is the definition of work. Remember, all work is a transfer of energy. Okay, so if I like lift a mass, if I exert a force upward for some distance, the mass goes from here to here. It now has some energy, and of course, it has potential energy, right? Okay, or if I throw it, if I exert a force to speed it up, its energy becomes this, and we can, I'm not going to derive that all again. Notice that this one's got a tricky theta in there, right? So really, when you get to grown-up physics, they'll say it's F dot S, okay? And that just means Fs cos theta. It's the scalar. It's a dot product. Okay, scalar meaning it doesn't have any direction. Okay, so and this angle is the angle between F and S. So if the famous example is if we've got the ground here and we're pulling a sled along the ground, as we commonly do. Nobody has these runner sleds anymore. They were wonderful. They went really fast, and if you wiped out with them, the sharp back edge of that could remove your kidney faster than a surgeon could. Anyway, this is the angle. So if we're exerting a force, say, in this direction, but the sled moves along the ground like that, right? There it is, right? So the closer they are to being parallel, the more this is just the cosine of 0, of course, is 1, right? Okay, and then if we're pulling straight up on it, but the sled happens to move to the side, we didn't do that, it was not us. Something else gave it energy or moved it. Anyway, so that's the work. This is the definition of work. And then there's something called the work energy theorem, which says that if you do work on a system, it will gain an energy equal to that amount of work. So in the case of a sled, it's gaining thermal energy dragging along the ground. In the case of something you're lifting, right? It's gaining potential energy. If you're throwing a ball, exerting a force over distance like a pitcher, right? Then you're giving it kinetic energy. If you're taking a string or a bow, as in a bow and arrow, and stretching it, it's going to be something like this, okay? But yeah, there it is. And then these are our energy equations. This is kinetic, right? And then this is this P squared over 2m. This is just plugging in P is mv, right? So P squared is just m squared v squared, right? And then all we have to do is divide that by 2m, and we've got 1/2 mv squared, right? Okay, and then this is our potential energy, gravitational potential. And they put changes in there because, anyway, you're not clever about your heights, right? And then here, finally, they've got the hooks. Is that H for hooks? I don't know, I'm guessing. The energy in a spring, right, is 1/2 kx squared. And notice here they have the delta x, and the whole thing is squared, right? Because that's the change in length. So just keep in mind, if you have a spring that's 10 centimeters and somebody stretches it to 12 centimeters, right? The delta x is going to be 0.02 meters is our delta x, right? Okay, so just be careful about that. They'll try to trip you up with that, and that's why it's got a delta on there. And that's why the Hooke's force should be minus k delta x. If they've got the delta here, they should have the delta there, but they're not always consistent. That's to keep you smart, It's not lack of attention on their part. Okay. And then this is our power equation. Thankfully, where's my cursor? There it is. Thankfully, they've included this one now. This is such a great help, okay, that it's work over time, but really it could be any energy over time, okay? So in one of the multiple choice questions I saw, they had a car speeding up, right? And it's like, okay, it's at rest and now it's moving. Well, the amount of work done was the kinetic energy that it has, right? Okay, so remember, work, this thing here, this work can be any change in energy. That's like a generic term. And then this is the time it takes, right? So you're going to end up with power in joules per second, okay? Watt is another term for joules per second. Okay, sorry. All right. And then force times velocity, that also works, right? Because remember, velocity is displacement over time, right? And so Fs, force times velocity is Fs over t, right? Which equals work over time, okay? So you can calculate it that way. I just hardly ever use that one, but there it is. And this one's actually pretty relevant because, um, when you think about the work that you need to do, the faster your car goes, the bigger the force is that opposes you, right? So if I drive to 12 and it's 70 miles per hour, there's going to be a whole lot more air friction acting against me. And I've noticed this, now that I have an electric car, it's like, oh, going fast really, really decreases my range. I think if you just take an ordinary thing like a Leaf or an ordinary run of the mill car, you can drive fantastic distances if you just go 25 miles per hour. And you can Google that. I'm not going to talk about that too much here. This is our efficiency, right? So it could be, I always did it with E, right? But our efficiency is whoa over we, right? Output over input, or po over p, e whoa we po p. Right? But then they made it all, it's like, did this, right? What do I do with that? I don't know if I can't make stupid jokes about that. It just makes me sad. But yeah, there we go. I'm just going to stop talking.